Aromatic hydrocarbons that are valuable feedstocks in the petrochemical industries are most commonly obtained from catalytic reforming of naphtha. The xylene isomers, ortho-xylene, Meta-xylene, and in particular para-xylene, are important chemical intermediates. Ortho-xylene is oxidized to make phthalic anhydride, which is used to make phthalate plasticizers. Meta-xylene is oxidized to produce isophthalic acid, which is used in unsaturated polyester resin. Para-xylene has the largest market of these three isomers. The demand for para-xylene is several times that of Meta-xylene and ortho-xylene. The largest use of para-xylene is in its oxidation to make terephthalic acid that is used in turn to make polymers such as polyethylene terephthalate and polybutylene terephthalate. PET is one of the largest volume polymers in the world and is used to produce fibers, resins, films, and blown beverage bottles. The objective of this presentation is to discuss the principles behind the separation of xylene isomers. The paraffins and naphthenes in straight-run naphtha are converted to desired aromatics in a catalytic reformer. The products from the catalytic reformer are sent to a raffinate splitter in which the top product consists of benzene, toluene, and some non-aromatics, and the bottom product are C8 hydrocarbons, ortho-xylene, Meta-xylene, para-xylene, and ethylbenzene, along with C9 aromatics. The bottom stream from the raffinate splitter is further distilled in a xylenes splitter, in which the top product consists of the C8 hydrocarbons, ortho-xylene, Meta-xylene, para-xylene, and ethylbenzene, and the bottom's product are the C9 aromatics. The mixture of C8 hydrocarbons is then sent to a unit that is called an SMB adsorber. SMB stands for simulated moving bed. The feed mixture is separated into two different streams. A raffinate stream consists of ortho-xylene, Meta-xylene, and ethylbenzene, and the extract stream consists of the para-xylene isomer that has the highest demand. And this para-xylene isomer is a feedstock to produce products such as PET and PBT. Let us examine the separation of C8 aromatics. The boiling points of the four C8 aromatics, ortho-xylene, Meta-xylene, para-xylene, and ethylbenzene, are very close to one another, and distillation separations are not feasible. However, there is a significant difference in the freezing points of the C8 aromatics. The component with the highest freezing point is para-xylene. And when the solution of C8 aromatics is cooled, the first crystals to come out of solution consist of para-xylene. This is because para-xylene stacks most efficiently to form crystals. Fractional crystallization is also a commercially viable technology for separating C8 aromatics. In this presentation, we consider the other alternative of separating the C8 aromatics by relying on entropy effects. Indeed, we shall look for adsorbents that rely on entropy effects to separate C8 aromatics. Now, para-xylene forms about 20% of the feed mixture that needs to be separated, and therefore we need adsorbents that selectively absorb para-xylene from the mixture. Commercial units employ simulated moving bed adsorbers, and in most of the technologies that are offered currently, Barium-X zeolite is used as adsorbent. The picture here is just to demonstrate that the separation of C8 aromatics in an adsorption device requires us to recognize the differences in the packing efficiencies of the C8 aromatics within the crystalline framework. It is analogous to stacking books in a bookshelf. In current industrial practice, the adsorbent used in simulated moving beds is Barium-X zeolite that has the Fauger-site topology that consists of cages of approximately 11 angstrom size that are separated from adjacent cages by 7.4 angstrom windows. A very good description of the separation of xylene isomers using Barium-X zeolite is available in the thesis of Costa that is available online. And I use the information and the figures from this thesis to illustrate a few points regarding entropy effects. Let's consider first the adsorption of Meta-xylene in Barium-X. Within a single alpha cage, the location of the first two molecules of Meta-xylene is relatively easy. But the location of a third molecule within the alpha cage is energy demanding because it requires a reorientation of the meta-isomer. The same is true for the ortho-isomer. In contrast to Meta-xylene, the placement of the third molecule of para-xylene within BAX is not energy demanding because the longer para-xylene molecule can be located in the plane of the window and is stabilized by interactions with the oxygen atoms of the framework. There is no corresponding absorption of meta-xylene or ortho-xylene at the window sites possible. So, summarizing, the difference in the absorption of meta-isomer and ortho-isomer with the para-isomer is that with the para-isomer, the loading of 3 molecules per cage is more easily achieved than with the ortho and the meta-isomer, for which the location of the third molecule per cage is an energy demanding task. The thesis of Costa contains an interesting and important graph showing the selectivity of para-xylene with respect to meta-xylene as a function of the total loading per alpha cage of faugisite zeolites. Blue represents Barium-X and the red symbols represent Sodium-X. For both these cation exchanged zeolites, the px to mx selectivity is the same up to a loading of 2 molecules per alpha cage. For Barium-X zeolite, the selectivity increases in favor of the para-isomer as the loading is increased beyond 2. This is because the placement of the third molecule of Meta-xylene is an energy demanding task, whereas the placement of the third molecule per cage, per alpha cage of para-xylene is relatively easy because the third molecule can be located in the plane of the windows. So the selectivity in favor of para-xylene is due to entropy effects. In a simulated moving bed adsorber, the feed of C8 aromatics is in the liquid phase And the essence of countercurrent contact between the liquid mixture and the solid adsorbent containing BaX zeolite is achieved by periodic switching of the inlet valves for the feed mixture, for the eluent that is commonly para-diethylbenzene, and the outlets of the raffinate phase and the extract phase containing essentially para-xylene. There are essentially 4 zones in the operation of an SMB adsorber. In zone 1, the adsorbent is regenerated. In zone 2, ortho-xylene, meta-xylene, and ethylbenzene are desorbed. In zone 3, para-xylene is adsorbed selectively. And in zone 4, the eluent para-diethylbenzene is recovered and recycled back into the adsorber. Since the adsorption selectivity is in favor of para-xylene that is obtainable with Barium-X zeolite is of the order of 2, it is of industrial importance to examine whether alternative materials such as zeolites and morphs offer improvements in para-xylene selectivity and uptake capacity. Let us examine a few candidate adsorbents, starting with AFI zeolite that consists of one-dimensional channels. The channel width is 7.3 angstrom at this position, and from groove to groove it's 8.4 angstrom. On examination of the molecular dimensions of ortho-xylene, meta-xylene, and para-xylene, it is possible to see that ortho-xylene can be located vertically within the grooves in a face-to-face packing that results in footprints that are very small. On the other hand, meta-xylene and para-xylene cannot be located vertically and occupy significantly longer footprints. Experimental data on the unary isotherms for ortho-xylene, meta-xylene, and para-xylene confirm that the saturation capacity for ortho-xylene is significantly larger than for the para and meta isomers. Therefore, mixture adsorption is selective to ortho-xylene, and this has been established in experimental data on transient breakthroughs. So it's possible to separate the xylene isomers using AFI zeolite but the absorption is orthoselective. Within the one-dimensional channels of mil-47, that is channels of 8.5 angstrom that are lozenge shaped, ortho-xylene can be stacked because the dimensions are commensurate with the channel dimensions. Here are computational snapshots showing the commensurate stacking of ortho-xylene within the 1D channel framework of mil-47. So it's possible to separate mixtures of xylenes, but the separation is not paraselective as we desire as alternative to Barium-X, but it's selective to ortho-xylene. For optimal stacking of para-xylene within an adsorbent, we need channel dimensions which are about 10 angstrom so that para-xylenes can stack vertically. One such candidate is the MOF MAF-X8 that has 10 angstrom channels, and the computational snapshots show that the para-xylene molecules can stack face to face in a vertical manner. And this is also evident in this movie animation.